Hi, everyone. So my presentation is called Embedding WebAssembly in OCaml' for Safe Program Construction. Okay. But I think that's a little bit hard to parse, so I'm going to rename it something that maybe is a little bit more resonant with the OCaml' community, which is making illegal WASM programs unrepresentable. My name is Hunter. I'm in the informatics PhD program at the University of Illinois. And for a little bit of context for this talk, WebAssembly is a low-level assembly-like language, but it's not all that low level, especially anymore. There's variable naming and other things that make it not that challenging to write by hand, or at least a little bit more friendly to read than a true assembly language. And so I want to make the point that nobody really writes HTML by hand anymore, right? We write fragments, we write templates, and we have ways of combining these things to construct the full pages that we actually send to the client. And so similarly, is it possible with good tooling to allow programmers to serialize their computations into WebAssembly and ship them somewhere else? That's kind of the research question I have, and the reason that I developed wasm-bindgen. If you don't buy that, that's okay. There are a couple other applications that I think this applies to. The wasm of OCaml' compiler allows for linking in WebAssembly binaries in the form of primitives. And then in the security space, there might be some interest in crafting exploits using a structure like this. So with that in mind, we want to make it easy for humans to write WebAssembly and construct large programs out of small fragments. And so to do that, we want to make sure that the DSL is easy to write, provides useful error messages, and most importantly, enforces safety. So there are a couple of libraries already in OCaml' that can represent WebAssembly, but they're more compiler-oriented. They use tall hierarchical structures to represent the code, and they don't do all that much to stop you at compile time, at OCaml' compile time, from doing something incorrect in terms of types, right? WebAssembly is a typed assembly language, and so if you leave your stack in an inconsistent state, the runtime, the embedder, will reject your program and it won't let you run. And there isn't really a good way to detect that at compile time, but we have the tools to do it. And there are other libraries in other languages that do this kind of thing, that allow you to build WebAssembly modules. Most notably, Rust's wasm-bindgen has a library for doing this, but it also doesn't enforce any kind of safety. So the goal here is to build a human-friendly representation of WebAssembly in OCaml' that can never generate an illegal, meaning type unsafe program. So just a little bit of context on WebAssembly, in case you're not familiar. It is a type-safe language. There are more than 4 types nowadays, but for our purposes, it's fine to just think about those. It's also a stack machine, which means that instructions are only concerned with what is on top of the stack. And before your module is allowed to execute, the runtime or the embedder makes sure that you're not doing anything illegal with the stack. Okay. So if you've built a language in OCaml' before, this probably looks pretty familiar to you. I stole it from real-world OCaml'. You might start building this GAT structure that represents your language, right? So you have expressions and types and things that you can combine together, and that's fine. But when you structure it like this, you start building this really tall tree of things together. So you might have some literals at the top, and then you combine them with a binary operator, and then a monop, and then that becomes a test expression, and you have this really tall structure that's like easy for compilers to deal with and compute on, but hard for people to think about. And so that doesn't really solve our problem here. We want something that's more flat and uniform that is easier for people to think about. And so that's a WebAssembly program, kind of. So we have our stack here and an I32 add instruction, which is expecting 2 I32s on top of the stack. And so when it executes jump, it takes those 2 off and then leaves 1 I32 on top of the stack, right? So we can sort of begin to characterize our instruction by what it expects on the stack and what it produces on the stack. Similarly, for an F32 negation instruction, it expects one F32 on the stack, eats it, and then leaves an F32 on the stack, right? So we're not too concerned with the actual computation that goes on with the instruction, just sort of how it manipulates the stack. Okay. So if we look at both of these, we can actually encode the state of the stack before and after in OCaml type, right? So we have these nested tuples or a cons lists kind of thing where we know that we need two I32s and then whatever the rest of the stack is, and then when the instruction is done executing, we have one I32 on top of whatever the stack was, and analogously for the negation. And we can put that in the types of a get that contains all of our instructions at one level. So we have two parameters in our instruction type here. The first one represents the input stack. The second one represents the output stack. So our I32 add that we just saw expects two I32s on the stack and leaves one. Our F32 neg expects one and leaves one. And the nice thing about this representation is that it is actually polymorphic or supports polymorphic instructions like drop. So drop can work on any of the four types, and we can just specify that with an A. So we have one thing on top of the stack, and when we're done, that thing is gone. So instructions by themselves are not programs. They're not super useful, so we need a small structure on top of them to sequence things together. So the instruction constructor there is basically just an introduction rule. The interesting thing here is the sequence type. So I have a program with A and B as its types, and then a instruction with B and C, and through transitivity, I know that I can create a program that takes in an A stack and produces a C stack. Okay. And then just for convenience, a little bit of notation and operator here to sequence instructions that I'll use a little bit later on. So having a sequence of instructions still is not enough to execute in WebAssembly. We need to create functions. And functions look like this in the monospace font there. And so it's going to be some set of parameters that we expect, some result that we expect, and some program in the middle that knows about the parameters and produces the result. So I say that this is stating a theorem because we say at the end I expect to have an F32. And so I need to make sure that whatever program is slotted into here produces an F32 or whatever the result ends up being. So that's our function. And so we define more data types to encode these. First, a stack type so that we can explicitly talk about what we expect as the inputs and the outputs. And then a block type, just for convenience, it's the signature of the function that we're working with. It pairs two stacks together, one for parameters, one for results. And then lastly, we have the func type, which takes in one of those block types for the parameters and the results. And then a program which starts empty, because WebAssembly functions always start with an empty stack. And then after it's done executing, produces a B-type stack, right, which matches our result type. So we are communicating or transferring what we expect in the function into our sequence of instructions and enforcing it. So there are a couple of problems with this. The first one is that if you encode all of your instructions that way, you get a huge get, which is a little bit unwieldy to work with. The other problem is that if you know anything about WebAssembly, there are local variables that I didn't talk about. So that's a third sort of member of the function, and they're pretty important to how functions work. They work a little bit like registers in that they have random access. So let's deal with that problem first. So back to our I32 add instruction, we know that it's executing in the context of a function, and we know that that function provides context or information about the locals that are there. So let's give our instruction an idea of the locals, okay? And so I32 add executes, it does the same thing. It knows the locals are there, but it doesn't do anything with them, and that's true for most instructions, right? But if I have a local instruction, it goes to execute, and it looks at its argument and says I'm looking for something in index 0, and I have something in index 0, so I can leave that on top of the stack. Okay, so that works great for index 0. It works for index 1. It does not work for index 2 because we ran out of locals. And so that would be an illegal instruction, and we want to avoid that. So how do we do that? Well, because each instruction is executing in a context where it needs to know what's around it, just like the input and the output stack, the context, we can just add the locals in there as a third type parameter. And so like we saw for most of the instructions, it just gets carried along. But it would be nice to have this local get instruction where we give it an integer, and it takes in some stack and puts a value on top of the stack, right? That unfortunately doesn't work because an integer is a runtime value and the local stack is a type. So it goes away when you compile. So, okay, fine. Can we at least reconstruct the case that we just saw, getting the thing at index 0? So we have this local get 0, where we know we're going to produce one thing, put one thing on the stack, and we know that our locals have at least one distinct thing, and then the rest of the stack. Okay. Then we induct on that, create local get 1, where we know that there's at least 2 things on the stack. So we don't care what the first one is. The second one in index 1 is of type A, and that's the one that we end up putting on our output stack. So talking to a PL crowd, maybe looking at numbers this way is not too bad. We're pretty used to it, but it's kind of bad. There's like pretty obvious limitations to this, right? So I kind of got stuck when I got here, and I was like, well, how bad is it, right? And the answer is, like, actually it is bad, but, so yeah, the WASM spec allows up to a full integer's worth of locals, right? So I don't want to write 4 billion constructors, but like that's what I would have to do. But there is this wasm-bench data set that we can take a look at. It has over 10 million real-world functions from over 8,000 modules. And what I found is that there's a pretty steep fall-off in the number of locals that are actually being used. It's a long tail, but it's a pretty steep fall off. And that spike there is at 32, which is kind of interesting, I think. So if I choose 32, that covers around 96% of these 10 million functions. And I think maybe that's okay. Handwritten functions don't seem like they would have a huge number of local variables. And if you did need more, it's relatively easy to just add more constructors. So one other thing, I lied a little bit. I said that locals were indexed from 0. It's not true. They're actually indexed from the first number that is not used to index a parameter. So the type, so what we need to be working with our local gets is actually parameters and locals concatenated. So the type of the parameters and locals concatenated here is pretty obvious, right? You can like take one thing and shove it in the other, and then you get 6 I32s. But in the general case, which is what the compiler thinks about, what is the type of concatenating 2 things? Well, unfortunately, the answer is it depends. And it depends is not a question that OCaml' can really deal with, right? This is the kind of thing that needs dependent types or would benefit from it, I think. So there are a couple of issues or solutions I'm exploring here with some kind of functor that takes in one of these types and uses it instead of the empty, and maybe some kind of delayed execution thing with CPS. But currently the solution is just to do manual concatenation, which is not great, but yeah. The other issue was that huge data structure. So we would need hundreds of constructors to support the entire language, and there would be so much rule writing you would have to do when you go to write like a stringify function or want to convert this to actual bytecode, right? So it's a little bit unwieldy to work with as a developer. The other little bit more subtle problem is that combining instruction sequences with mismatched types becomes difficult. So what I mean by that is we want to be able to compose things, right? And so if we have this fragment on the left, it results in an I32 on the stack, and then the fragment on the right accepts an I32. These things match, so it's good. We can concatenate them. But in an instance where I want to add two constants and then add two more constants and then add the results of those, the stack types no longer line up, and we can't do the concatenation anymore. So we could fix this by introducing some kind of like state constructor and using that in place of the empties up there. But that's a little bit fragile, and we might not always know what it's supposed to look like. And then the other problem is that when we are combining two programs, we start building trees, and that's sort of the problem we were trying to avoid in the beginning. So fixing the large instruction data structure and this concatenation problem both together, we turn to combinators. So this is what our instruction type looked like. We're going to drop the specific types from each of the instruction, just make them generics. We're also going to remove the names from each of the instructions. And then we're going to add back in a value type that carries, the type that we're supposed to be working on here, so that a value matches the a in the input and output stack. So we're still ensuring type safety through the compiler, but it's a little bit less explicit in the instructions. So this technically lets us encode non-existent instructions, right? There are some instructions that are like specific to integers, and I could just pass in an F32 value if I wanted to, and we don't want users doing that. So instead of using the types to precisely describe the instructions, we can limit what's allowed to be constructed using functions, and combinator functions specifically, and that looks like this. So each of these take in a program and then produce a program back out. We have all of our types enforcing the correct things in the right places. And each of these, just basically sequences the instruction in its own name with the correct type. Okay. So as long as we use these, our programs are going to stay legal. The other issue was combining sequences of instructions, and for this, things get a little bit more complicated. So the issue was that we have like a cons list, basically, of instructions, right? And you can't append to a cons list because it's buried all the way at the end. So instead of constructing it, when you define it, what if we delay it a little bit until we're sure that we have all the instructions we want in the sequence? We can do that with continuation passing style. So the example that we saw before, rewritten in continuation passing style, it's possible that you may not enjoy programming like this, which is okay because it's relatively formulaic, and I think pretty easy to introduce functions or operators that hide a lot of this, but I think it's helpful to see what it looks like. And so using this, we can combine fragment A and fragment B, and then signal that we're done using the ID function all the way at the end. And with this, our types line up, and we get one single list structure, basically, of all of our sequences, or all of our instructions. So looking at sort of a real-world, larger program, this is what it looks like. It is in continuation passing style, which I know is a little bit hard to read. But what we're looking at here is a OCaml' function that accepts a fragment of wasm-l that takes in an I32 and returns an I32, and then inserts it into an iteration function, basically. So you can think of this kind of like constructing map. Okay, if you write your function for map in wasm-l, you can pass it in here, and then you get back a WebAssembly function that takes a memory address and applies the function to it. Don't look too closely at that because it is an infinite loop. I wrote it at 1 in the morning. But it gives you an idea of generally what the structure of this looks like. And if you squint, it kind of looks like WebAssembly. Okay, so sort of where this is going, right? We saw a little bit of custom function generation. I think there's a lot more to do in that space, but figuring out the idioms to make it happen is a little bit of a challenge. So a concrete example, you might have a dot product that you want to do where you know the weights, but you don't know the parameters. And so can you generate some kind of function that avoids any unnecessary multiplication or addition based on, if things are 0 or 1, right? That also is a bit of a challenge. because you end up with polymorphic types sort of internally. If you don't put an I32 on the stack in one branch, but you do on another stack, it's like a little bit hard to deal with. But this sort of like just-in-time or very custom code generation, I think it is another potential application here. So to wrap up, wasm-ml uses OCaml's type system to make illegal WASM programs unrepresentable. It prevents them from being it prevents the OCaml' program that contains it from being compiled. Or maybe not unrepresentable, but at least difficult to represent, right? In the future, I think complex combinations of program fragments will help support research on using WebAssembly as a serialization format for computations. The abstractions that we in the PL community love to build and use are often too language specific to really interoperate with each other. So in the same way that JSON and CSV have become sort of the default data interchange formats, I think we need to go to a low common denominator sort of description of computation in order to really get things to work together. And to facilitate that, I built this to hopefully give people the tools to build safe representations of computation that can be combined. That's all I have. Thanks for your time.
Yeah, thank you, Hunter. Any questions?
Thank you very much. It was very interesting, and it's an impressive usage of GADTs. I remember that in the Thesis code base, they use a smart contract language called Michelson, which was a stack-based language. And I quite remember that there is a very, very impressive intermediate representation that deal with a kind of encoding that you use, so using tagless final representation of CPS inside the type system. And I guess that they fix some issue with local and indexation using piano arithmetic at the type level. So I remember that it was very hard to work with that kind of function because, yes, it was one on the goal of the presentation, but even you can have a set of Michelson program valid by construction, error are extremely hard to read. So do you was aware about this implementation and how you will fix error when you deal with a lot of indexation in your GADTs?
Yeah, I wasn't familiar with it, but you're asking about the errors that the compiler produces when you have a problem? Yeah. So they look quite a bit like the types, right? That's the level that you're dealing with. And sometimes they do end up being a little bit gnarly to look at. And so I think, I was talking a little bit about you have to understand the idioms you need to work with this kind of language. And so you can see here that I've built and named a lot of small fragments. And so working sort of piecewise, I think is maybe the best that we can do right now.
Yeah, thanks.
Any other questions? Yeah, thanks for the talk. Once you start being able to build this kind of program, are you able to then do any optimizations at the when it gets compiled down to WASM?
No, and I don't foresee doing that in the future. This is not meant to build compilers. It's meant to enable people to write code at a lower level than what they're used to. And so, the area that I work in is research software engineering, particularly on smaller data sets where researchers don't have a lot of compute knowledge or resources, but maybe want to adopt the computational techniques. And so optimization is less important than clear communication in those cases. So not a goal right now.
Thank you.
Any more questions? I have a question. Yeah. So in one of your slides, you said the concatenation, when you do the concatenation, it depends the type. So what's the reason for that?
let me find the, there we go. Yeah, so when you want it, so I'm in this list notation, these are not actually lists. Okay, I rewrote my own data structure. There we go. To do this, so that empty list case ends up being an empty stack. That's a concrete type, and that means that at the end you can have nothing other than an empty stack. So you can't stick in another, stack that you want to build on top of. It ends up being a type level function, not one that can be computed at runtime.
Okay, thank you. Yeah, one.
Yeah, great talk. Very cool. So you had that one situation where you really needed natural numbers in the types, but you ended up having to blow it out into 1, 2, 3, or 5, etc. I was wondering if you had any other properties you really wanted to encode that you ended up not being able to encode at all. Because that one you kind of solved it, but.
Yeah, I mean, the counting issue shows up in other places in WebAssembly, right? Blocks and breaking is the other one that I can think of, right? So it's difficult to restrict somebody to only using an index for a block that's already been declared. I think you would have to go about it the same way, but yeah, it's a recurrent problem in a couple places here, and that's the best I have right now.
So maybe you need dependent ML with the index.
Yeah.
Nice.
Thank you, Hunter. So thanks for the nice presentation.
Thanks.